Okay, let's look at another root locus example. Here we've got a closed loop system. We've got a proportional gain and a plant in here, 1 over s plus or s times s plus 2. And so we want to look at the root locus. Remember, we are going to be looking at the open loop system, and so we're looking at creating the root locus for the k over s times s plus 2. So first thing we're going to do is we're going to look and factor the plant or the transfer function into first and second order systems, which is already done for us in this case. And so then we're going to plot the poles and zeros. And so in this case, we've got a pole at 0 and we've got a pole at 2 or minus 2. And so we've got those two poles. That's all we have. We don't have any zeros in this case. And so the next thing we're going to do is look at where on the real axis do we have the root locus. And so we use the pin up, pin down. We start at the origin with our pin up, and every time we see a pole or a zero, we're going to put our pin down or pin up, whatever it's not. And so I start at the origin and immediately see a pole, so I put my pin down and I draw till I find another pole, and I lift my pin up, and that's going to be the root locus along the real axis. Now we next are going to be thinking about where these poles are going and or where these locus are going. They can't just terminate there. They have to go somewhere. And if we think about it, we've got two poles, no zeros, so we have two of the locus branches going to infinity. And we know that'll be at plus n minus 90 degrees. But where those asymptotic lines intersect the real axis, we need to calculate, and so we're going to use the equation sum of the poles minus the sum of the zeros divided by the number of poles minus the number of zeros. And so the sum of the poles, we've got 0 and we've got a minus 2, and so that's going to give our sum of our poles, and minus 0 going to be the sum of our zeros, and we've got two poles and no zeros, and so what we end up with is 1 and from our calculation, and that tells us where on the real axis the asymptotic lines intersect. And so we come in here at 1, and that's going to be the intersection, and so we've got our asymptotic lines that are going to go plus or minus 90, and so these locus are going to come out. They're going to originate at the open loop poles. They're going to come towards each other. Then they're going to split, and they're going to move along these asymptotic lines and go to infinity. And so that is our root locus for this system. Now, just as important as developing the root locus is interpreting the root locus. What does this mean? Remember, we're going from a gain of 0 to infinity. So as we turn our gain way down to 0, the closed loop poles are going to lie on the open loop pole. So we're going to have a closed loop pole at 0 and a closed loop pole at minus 2. So what we're going to see is two first order systems. It's going to be an overdamped system, and it's going to be fairly sluggish. But then as we turn the gain up, these two poles, the closed loop poles, are going to move together, and eventually they're going to meet, and we're going to have two closed loop poles at minus 1. And this is going to be critically damped. This is the fastest it can get without having any overshoot. And so we're going to see that as the gain gets turned up. And then if we continue to turn the gain up, the closed loop poles are going to move off of the real axis into the complex plane and start oscillating. And the higher we turn the gain up, the more they're going to oscillate. And so we can think about this, and if we're trying to tune this system, we would recognize that from a low gain, we could probably improve the performance somewhat, and then, but then if we try to turn the gain up even more, we're going to get that initial oscillation at the transient point in there. And so that is the root locus and the interpretation of that system.